In this video, I'm just going to talk about some integration things that are kind of unique for these questions. They're not like your normal plug in the rule and get your answer type of problems. They're a bit more unique and require a bit more thinking. So I'm just going to talk about a few examples that kind of encapsulate most of the ones that you might come across. This first one here, we have the integral of square root of x dx. Now, as we look at this, we might recognize that there's no actual rule for the integral of the square root of something. But what we have to recognize in this case is that sometimes you don't get an equation that you want to integrate in a form that makes it easy for you. In this case, we actually have to change the form to make it recognizable to us as something we have a rule for. In this case, what we do is we rewrite the square root as x to the power of 1/2. Now that we have it in the form x to the power of something, we can simply just use the power rule. So what we do is we apply the power rule, we add 1 to our current power, so we get x to the power of 1/2 plus 1, and then we divide by that new power, which is 1/2 plus 1. And it's not a definite integral, so we don't need to substitute in bounds. This will just be the rule, plus c on the outside, and we'll just simplify everything. So we've got x to the power of 1/2 plus 1. 1/2 plus 1 is 3 over 2. So we divide by 1/2 plus 1 as well. Now we divide by 3 over 2. That's the same as multiplying by 2 over 3. So this simplifies down to 2 over 3 multiplied by x to the power of 3 over 2 plus c on the outside. So in that case, it wasn't in the form that we recognized, but we could convert it into a form just by changing the square root to a power. Now it's very similar to this next problem, except it is in a form that we recognize. I think that this form just looks slightly different to, let's say, if you had something like x squared. So I think a lot of people get confused with this, but it's exactly the same rule regardless of what the power is, whether it be positive, whether it be negative, whether it be a fraction. So again, you just apply exactly the same rule. So we add 1 to our power, x to the power of negative 1/3 plus 1, and then we divide by negative 1/3 plus 1 as well. Then we substitute in our bounds, 0 and 1. Now when we're evaluating definite integrals, we don't need the plus c because the plus c makes no difference to our definite integral. We're going to add c, and then when we substitute in our second bound, we just minus c anyway. So there's no point including the plus c. So that's for definite integrals only. Awesome. So now let's simplify our expression before we substitute in our bounds. So we got x to the power of negative 1/3 plus 1. So that becomes x to the power of 2/3. Then we divide by that power as well. And then this would be 1 and 0. Now, same as the previous question, dividing by 2 over 3 is the same as multiplying by the reciprocal of that, which is 3 over 2. So I just put 3 over 2 here. Now let's substitute in the bounds. 3 over 2 multiplied by 1 to the power of 2/3 minus 0 to the power of 2/3. We should recognize that the powers make no difference to the numbers. 1 to the power of anything is 1. 0 to the power of anything is also 0. So we just get 3 over 2 multiplied by 1 minus 0, which is equal to 3 over 2. Now, for this last example, we're asked to evaluate the integral from 0 to infinity of e to the power of negative x dx. Now, probably up until now, whenever we had infinity in a calculation, usually that meant that something went wrong or you're at an asymptote. Now, in this case, for integrals, sometimes infinity is actually useful, and sometimes it's something that we can actually put a number towards, which is kind of counterintuitive to what we've learnt before, but using a graphical explanation, it might make a bit more sense. What I've got on this plane here is the graph of e to the power of negative x. I've drawn in the coordinate 0, 1. This is essentially the starting point of our integral, and we're asked to evaluate this from 0 to infinity. Now, infinity has no number associated with it. However, we can see that we have an asymptote at y is equal to 0 for this graph. So as x approaches infinity, y approaches 0. Okay, that's the observation that I make from this graph. So let's start evaluating e to the power of negative x, and let's see what we get in our calculations. Let's just erase that. I might just move that to the side because that's actually pretty important. So as x approaches infinity, essentially as x increases, y approaches 0. That's kind of what the arrow indicates. Now if I evaluate the integral, it would be negative e to the power of negative x with bounds infinity and 0. I know that if I have a negative, I could take that out and just swap the bounds. So it'd be 0, infinity. Now in this case, it's e to the power of negative 0 minus e to the power of negative infinity. Okay, so e to the power of negative 0 we should just recognize as 1. Now e to the power of negative infinity, what I'm going to do to try and evaluate that or put a number to that is just sketch e to the power of x, or you can think of e to the power of negative x. Since e to the power of negative x is already here, I'll just think about e to the power of negative x when x is equal to infinity. So as mentioned before, as x approaches infinity for e to the power of negative x, y approaches 0. Now for integrals, you're allowed to use this, I guess, assumption or observation to say that this just becomes 0. And that's perfectly fine in this case. Although e to the power of negative infinity doesn't inherently equal 0 as a number, we can see that from the graph, it eventually becomes this value as a limit. So what I could say is this just becomes 1 minus 0, which is equal to 1. Now in this situation, it's perfectly fine. And for any integral situations where you have something approaching an asymptote where it kind of converges to a certain value or plateaus to a certain value, it's perfectly fine to make that assumption just based on the graphical depiction of where the value is approaching. So in this case, e to the power of negative infinity, as x approaches infinity, y approaches 0, so I could just cancel this out as 0.